Alright, so in this video we look at an example of the fundamental theorem of line integrals. And recall that the fundamental theorem of line integrals is essentially a method for computing a line integral of a vector field if that vector field is of a very special nature that the vector field f, if it's the gradient of some function v or the gradient of some function phi, v equal to phi, called a potential function. Okay, now we'll get into details later in later videos about how to compute this potential function. So there are some questions here, like how do you know that a vector field has a potential function? Like once you know that a vector field has a potential function, how do you go about finding it? And in later videos we will discuss that. Okay, but in this video I want to just focus on an example, assuming that we know that a potential function exists. Okay, so here's an example that we have done in the past. Okay, so let's make some observations here. We have a vector field given, and this vector field is equal to 2xy, x squared minus 1. So here's a given vector field, and our curve C is the top half of a circle of radius 1, and we're seeing that down there in the figure on the left, okay, right here. Okay, and we're integrating from this point to this point inside of the vector field 2xy, comma x squared minus 1. Okay, now what we're adding to this problem is now that this vector field f actually has a potential function, x squared y minus y. And you might want to ask where that comes from, but let's just make an observation and let's just note that v is a potential function because if you look at the gradient of the potential function, take those two partial derivatives, those constitute the gradient of this function. If you compute the gradient of that function, v, the partial derivative with respect to x is equal to 2xy. The partial of that same function v with respect to y is equal to x squared minus 1, which is in fact the vector field f. Okay, so without knowing exactly where this vector field is coming from, we need to talk a little bit more about that. Okay, but assuming that the vector field, you know the potential function for it, or that it is given to you, we can now use the fundamental theorem of line integrals to evaluate this vector field along the curve. And in the past, we have evaluated that equal to 0 using the definition of the work integral. Okay, so we've done that in a previous video. So we know that the answer comes out to be 0. Okay, but given the fact that this vector field is the gradient of some function v, a potential function, and we know v is known, v is equal to x squared y minus y, we know that we can then do the fundamental theorem of line integrals to evaluate the potential function at the endpoint of the curve. Okay, and the endpoint of the curve, since we were integrating from 0 to pi, when t is equal to 0 and t is equal to pi, this is our a value, this is our b value, the curve evaluated at b, right? The curve evaluated at b is the point (-1, 0), and the curve evaluated at a is equal to 1, 0. So here is our point Q, here is our point P, P, and Q. Okay, we now need to evaluate the potential function evaluated at the point P is the point P is x is equal to 1, y is equal to 0. So if you take x squared y minus y and evaluate it at x is equal to 1, y is equal to 0, you will get 0. The potential function at the point Q is the same function x squared y minus y evaluated at -1, 0. And because y is equal to 0, this potential function will come out to be 0 again. So to evaluate the line integral, you need to do the potential difference. Okay, and so you'll get 0 minus 0, which is 0. Okay, so there we have, according to the fundamental theorem of line integrals, the same value of the integral, but through a potential difference. Okay, so what we can see in this example, okay, I've taken the same vector field in both cases and just adjusted the curve. So in the first example, we looked at the line integral along the top half of a circle. Okay, so let's try another example here. Okay, now we're going to keep the same vector field. Okay, the same vector field, and that means that we still have the same potential function, x squared y minus y. Okay, so if we now change the curve to be the straight line from the point P, here's a point P, okay, this will be the straight line from 1, 0 to the point Q is equal to 0, 1. Okay, here's the point Q. Okay, and we are asked now to compute the line integral along the straight line inside of the same vector field. Okay, so we're now going to compute the work moving from point P to point Q along a straight line. Okay, now we know by the path independence nature of these line integrals that we're likely to not get the same answer. Okay, because we changed our path. Okay, so let's see what happens. Now that we know we have a potential difference, we need to evaluate the potential function at the point Q minus the potential function at the point P. And again, we're using this, the fundamental theorem of line integrals, because we know the vector field is the gradient of some function b. And so only because we have this potential function is this result going to be true, that this vector field is the gradient or the derivative of some function. Okay, so if we evaluate our potential function at Q minus the potential function at P, you will get x is equal to 0, x is equal to 1, y is equal to 0. Okay, so you'll get minus 0, but it's this part right here where we actually get Q is equal to 0, 1. So when x is 0 and y is 1, we'll get -1. Right? So -1 minus 0 is -1. And that will be the answer that you get when you compute the line integral along the straight line. If you compute it from definition, there's your vector field along your curve. Okay, this is what you'll get by doing the Calc 1 line integral, and you will also get -1 for the answer. The potential difference also gives you -1. Okay, so the fact that we had a vector field which had a potential function, it allowed us to be a little bit smarter about evaluating the line integral of a vector field, and we did that using the potential difference.